Okay, gentlemen, that was very informative, and we appreciate you making the trip to Dayton and making your presentation. Ed Collins told me on that tour for tomorrow, he's got the sign-up sheet back by the coffee, and I see a hand back there.
Yes. Several of the slides said proprietary information.
Oh, sorry.
It's now been streamed on the internet. What is proprietary?
It's not proprietary, I'm sorry. They were copied from another internal presentation, but those slides I saw are not.
So the proprietary does not apply?
No, they're not.
I suggest that proprietary be removed before they're posted. Somebody might change their mind.
Okay, our next speaker is Deirdre Beggs. I guess I got that right.
Deirdre.
And who?
Deirdre.
There we go. Anyhow, these young people here are going to be talking about mitigating Earth to space propagation effects through adaptive waveform switching. That's quite a topic there for you guys there. So anyhow,
He's just helping me out. This is Andrew Rogers. He's my, buddy. We're good? We're good to go?
Yeah, we can do it this week.
Oh, so this is laser point. Okay, cool. Excellent. So like he said, I'm Deirdre Beggs. I'm one of Dr. McGuire's students. I like to say I'm the kid sister of all the other people that you've seen at UMC.
Closer to the mic, honey.
Closer to the mic? Okay.
There you go.
Thank you. So this is my master's research that I'm working on, and it came about because I walked into Dr. McGuire's office back I think a year and a half ago, 2 years ago, and I said, I don't really know what I'm interested in, but I think NASA's pretty cool. So then Dr. McGuire threw me on this project. We got to travel up to Cleveland, and when we were there, we actually saw the NASA scan testbed, which is what I'll be working on, which is on the ISS. We saw them having issues where the solar panel came into view of where the antenna was, so we were kind of getting some blockage with the receiving. So that kind of was the motivation behind this project, is that there are lots of different propagation effects, as we're well aware, with space communications. And in addition, the solar panel shadowing kind of led it to me thinking that we should do adaptive waveform switching between modulation schemes. So the setup of my experiment is I'll be adapting the uplink with different modulation schemes. The downlink will be a simple BPSK transmitter. And on the NASA scan testbed, I'll be programming an FPGA receiver, which is scary, to switch between modulation schemes.
Who made it?
JPL. The JPL SDR. There's 3 radios on NASA scan, but I'm working on the JPL SDR. So this beautiful picture here is made in STK, and I like it because it gives you the visual of we're looking through the solar panel to see Glenn Research Station. So let's get my solar. Okay, so NASA is right there, and the antenna that we have, I have just a general pattern because I don't have the JPL SDR antenna pattern yet, so I just put it up there so we could visualize exactly where the antenna is. And so my 2 goals for my master's is to model the Earth to space propagation environment, as well as then, after I have my model, develop an adaptive waveform switching algorithm. Alright, so the cool thing that I got to do is I got the Learning Systems Toolkit, which Andrew actually was the one that brought me up to speed on that, being awesome in aerospacey. So this is just the general visual interface for it. We've got a 3D view of the globe, we have 2D, and then this is my favorite, the obscuration tool. But I'll go into detail with each of these now. So the SDK 2D interface just gives you the orbit track, and the lines right here, those are each time that the ISS will be passing over the Glenn Research Station and have access to it, so that we'll be able to see each other and transmit. And then here's just the global view, so we can see that currently the ISS is visible to Glenn Research. And then this one is my favorite. It's a video, so let's hope it works. So this is just, we're looking down the antenna bore site of the JPL SDR, and as we can see, the solar panels are moving through the view. So if our Glen Research Station was right here, then we're going to be blocked, and our transmission will not be received as well as it could be. So in the propagation modeling, we have path loss, we have shadowing, which is from the solar panels, and then Doppler effect is something that we always have to consider when there's a moving receiver. And then additionally, I added in atmospheric and ionospheric losses, as well as the transmitter and receiver hardware losses. So I'm not going to go into the math too much because it's Saturday and it's early and we're not going to do that. But I'm going to give the breakdown. So this is the Glen ground station specs, and the thing you need to know about this is we're getting about 32.5 dB of gain from our antenna, so pretty solid. And the path loss, I did a whole bunch of models in STK. STK allows you to look at a whole bunch of passes when you're visible to the ground station. So I was able to pull out the minimum and maximum values of path loss. So minimum, we're looking at about 151 dB, and maximum, we're looking at about 166. So here are two graphs of the path loss. The one on the left is just the JPL SDR's access to the ISS because it is not on a gimbal, so it cannot track the ground station as you're going overhead. So that's the one on the left. The one on the right is just the entire International Space Station, so it makes this nice little curve, which I think looks better than the JPL one, but gotta work with what you got. So here's the link budget. The link budget, I simply did that so I could figure out what the maximum minimum carrier to noise ratios are. So minimum, we're looking at 25 dB, and maximum, we're looking at 40.4. So when we have a really good receiver or a really good link, we're pretty much able to transmit any modulation scheme. There isn't any issue with high bit error rate or anything. And then Doppler shift, again, we're looking at a maximum of 50 kilohertz and a minimum of -50. So we're going to be adapting that at the transmitter, similar to a lot of what ham radios do, because we can't be changing that on the JPL SDR because other people might be using it. So again, this is just, left is the JPL SDR's access to Glen, and then the right is the entire ISS. This is just another view of the shadowing. So I needed to figure out, the hard part about this is figuring out how to determine when shadowing is occurring. So to use this, I did use the obscuration tool because it gives the percentage that's blocked from your viewpoint. So the red circle I put just as kind of a reference to see as the solar panel is moving through. You can see that the blue is obstructed and the yellow is free visible. So I used this in my model to trigger, like if it's above, say, 40% obstructed, then that I would consider shadowing and take an additional 10 dB off of the link calculations. So with all those different model effects, I then plotted, this is like getting into the work in progress stage. So this is the theory behind how I want my waveform switching to work. I picked a bit error rate threshold of 10 to the -4. It's kind of an arbitrary value I picked right now. I'm looking for more backup for why I want that to be the threshold for bit error rate, but for now it's just for simulation purposes. So the different modulation schemes I'm looking at are BPSK, QPSK, 8PSK, 16 QAM, and 64 QAM. So the theory behind this is, say that we're operating at 30 dB, and so we're in 64 QAM, everything's going great, but then the solar panel moves into view and it takes 10 dB off. So now we're operating in about 20 dB, which then means we can bump back to 16 QAM. So we lose data rate and we lose, like the amount of data we can transmit, but we're still maintaining fidelity with our data. So it's kind of a trade-off on that, and I'm trying to find the ideal place to switch. The other issue with this is I have to make sure that we're not switching, like, you know, we're right on the border between 16 QAM and 8 PSK. I don't want to be switching back and forth every, you know, like 5 seconds, because that's just not going to be useful, because I'll have to communicate to the transmitter and tell it to switch, and so then you have all that delay. So I'm making sure that there's not oscillation between switching with the mod schemes. So my next steps for this, as it's still work in progress, I'm working on finishing the mod schemes and doing all the performance simulations for that. And then as well, I'm working on the development of the receiver to put on the JPL SDR, which means I get to learn FPGA, which is an exciting thing. And then I'm hoping later in the year, December, fingers crossed, I'll be flying on the ISS to actually evaluate the performance with my simulations that I have. And just for fun, here is the in-progress receiver design, and it's, you know, it's exciting, I guess. And then I'm working on a digital automatic gain control. But with that, does anyone have questions?
How did you pick adaptive?
So how do we perceive adaptive waveform switching better than predictive? Do we have uncertainty on the exact position and orientation of ISS?
I think we picked adaptive because we're not going to be able to put the information on the ISS saying, oh, well, we're going to be expecting the solar panel to be rotating here, so instead we're going to be measuring either the received energy or the bit error rate at the receiver, and then if we notice that it goes above our threshold, then we will transmit to the ground and tell it that we need to switch in order to keep our values the way that we want them.
Stay put.
Oh.
A quick one. The size of the dish at S-Pen, about a meter?
On the ground, it's 2.4 meters.
Upstairs.
That I'm not sure of.
Anybody else?
The antenna on the ISS is an omni. It's a very low directionality. So there is no traditional port ISS, and there is no pointing capability. It's just an omni sticking off the side.
Oh, well, she had a thing that said that gain on the dish was about, the gain on the antenna on the ISS was.
No, on the ground.
Yeah, that was the ground antenna.
Because I calculated that 1 meter would give you that same gain. You guys, 2.4, you should be getting a little better.
All right, well, I will double check my calculations on that then. Thank you.
I just offer this as a possible help. I don't know.
Mm-hmm.
I work with NEC a lot. They do microwave links, and they use adaptive modulation because they can't tell when the rain's going to come, when the fog's going to come, when the atmosphere's going to bend the beam.
Mm-hmm.
They have the same type of problems, and they do this on the fly. They go from like 128 QAM all the way down to BPSK.
Right.
Now, I don't know if they have something, if they'll talk. I'm just offering to you that they seem to be good at that.
Okay, and what was the name?
Nippon Electric Corporation. They're like the second largest manufacturer of microwave links.
Awesome, thank you. I will look into that. No more questions? All right, thank y'all.